Okay, now let's write the d sub 1. The d sub 1 is, what was this? This is 185 mm, and our d sub 2 is 280 mm. Okay, so let's substitute all the values to obtain the belt length. So 2 times 1000 plus 1.57 times the sum of d sub 1 and d sub 2. 280. So this is 465. Okay, plus the third term, d sub 1, 180 minus, sorry, 185 minus 280 squared divided by 4. What's the 4c? 4 times 1000. And this is 2.26. Okay, so let's add this all together. 2.26 plus 1.57 times 465 plus 2 times 1000, that is 2000. So we have a belt length of 2732.3 mm. And take note that as I've said in the lecture discussions, that the specifications or the designation for belt length, like for example B60 or B45, it's actually given in terms of inch. So we have to divide this. Let's divide this by 25.4. Okay, so we have L is equal to 107.57. That's inches. And we still have to round this up to some reasonable values. And right here in our table 10, so we have here the length designation. So we have to find this 107.57. So that's around here. Okay, so we have 97, we have 105, we have 112. So let's just select 105. Okay, so let's just let's write it here. So from table 10, select 105 mm. Oh, sorry, this is not mm. This select L. L is equal to 105. Okay, next step is to determine the number of belts. So, determine the number of belts. And we have this equation that N is equal to the design power divided by the corrected power. Okay, which is just equal to, this one is just equal to the power capacity of the belt, that's P sub B, times the correction factors for the arc of contact, and then the correction factors for the belt length. Okay, so let's find PB first. Okay, so PB can be obtained from table 4. Okay, so here's our table 4. So it says here power ratings for section B V belts, because we have computed that our belt type is a type B. You would notice right here in the first column that this is the RPM of the small pulley, and right here is the pitch diameter. So whatever the line, whatever it would be the intersection of the lines, then that's gonna be our power capacity of the belt. Of course, we're just referring to one belt. And another set right here is, it says here, additional power per belt for speed ratio. So that's why we computed our belt ratio, because we need to find the additional power that's given right here. Okay, so recall that our RPM for the small pulley is 1750, right? So we have here 200, this is 870. Okay, actually you would notice that sometimes this is not in order, uh, of of increasing order, because this is 200, this is 870, and then this is 400. So we just have to check it. Okay, so here it is. We have here the 1700. This is the 1750. So let's put a line, and the pitch diameter, since we assume a 185, right, then it's gonna be this value. Okay, so that's 6174 watts per belt. And for the additional power per belt, let's determine first uh, our speed ratio, and we computed our speed ratio as 1.45. So this will be the range, 1.35 to 1.51. Here's the range. Let's extend this line. So here it is. Okay, that's 433. Okay, so piece of B is equal to 6,174 plus this value, 433. So 6,174 plus 433. That is 6,607 watts. And of course, this is only for one belt. Okay, let's find now the correction factor. So C theta. Okay, so C theta can be obtained from table 9. And by the way, let's write here 6.1, and this is 6.2. Okay, and here's our table 9, and you can see here that there's the arc of contact in degrees. So if we know our arc of contact, then we can solve for the correction factors, or we can obtain the correction factors. And we can solve for this arc of contact using this equation. Theta is equal to 180 minus 60 degrees times t sub 1 minus t sub 2, and that's that's absolute, I guess, or the larger. Let's just use absolute values, divided by the center distance. Okay, so this is our equations, and for our center distance, this is 1000 mm. That's our tentative case. And when we solve this is 107.57, but we rounded this up. We changed this value to some standard lengths. So it is also possible that we use here the corrected center distance if we'd like. However, my reason right here is that since we still have allowance for take up, and there's also some motor base that's that that has this that provides some take up allowance, and also we can use idlers if we want, then I'll just use this assumed center distance, right? So 180 minus 60 degrees times the difference between the two diameters, that's 280 minus 185, because it's just absolute, divided by 1000. And we have here 174.3 degrees, right? And therefore from table 9 we have here 174. Then what's our correction factor? This is 0.99. Therefore this factor is equal to 0.99. Okay, next is to solve for this one, for the for C sub L. Right now for the C sub L, so solving for C sub L using table 10. Okay, so right here's our table 10, and here's our belt length, right? This is the 105, and right here's the belt correction factor. Okay, and we have this type B, and therefore it's gonna be this value. This is 1.04. Okay, so C sub L is equal to 1.04. Therefore the corrected power capacity is P core is equal to P sub B times these factors, and if we substitute the values we have, this is 6,607 watts times this factor, which is 0.99, and times this factor, which is 1.04. So this is 6,802.56 watts. And therefore, okay, 6.5. The number of belts is, we have this equation P sub D, that's the design power, divided by the corrected power capacity. Okay, the design power is 9,694.1 watts, divided by this 6,802.56. Okay, so 9,694.1 divided by this, we have 1.42 belts, or 1.43 belts, but of course we have to round off to whole numbers. Okay, so therefore N is equal to 2 belts. Okay, so far we have completed already the design, because we have let's write it here. So summary, we have the type B V belts, right? So belts, let's just write here. We have type B, and what else? The length is 105 L105. Actually, that's not L105, but rather B-105. Okay, let's just write here the length is equal to 105, and then also two belts. And for the pulleys, we have d sub 1 is equal to, what was that, 180, 180 mm, and d sub 2 is equal to 285. Oh, sorry, this is 285, 185, and this is 280 mm. Okay, so in terms of how we specify it, this would be I think B105, and this one would be in terms of the diameter and also the number of grooves and the bore size. So by the way, when we select pulleys, we really have to check if our bore diameter would fit, because right here in this figure, here's actually the bore diameter, and it's designated as letter D. Now if you check here the specifications, so if we have type B pulley, then we have to check this bore diameter, so we only have this range, which is 16 to 30 mm. Okay, so that means that we also have to check this one so that we can fit with the shaft, because sometimes when we compute, or as I've said, that since this is a design, then there's a lot of possibilities or pulley combinations that can do the job. But sometimes if you use a very small pulley, then maybe this will be the problem, the bore size. Because if you have a small pulley, then of course the bore size would would also uh, would also become small, right? So just like this one, 12 to 21 mm. Okay, so let's just use 25 mm. So this would be 185. Okay, diameter by bore size. The bore size is let's say 25 mm. Okay, by the number of grooves, this is 2b. And actually, as I've said, that sometimes it's actually in terms of inches, so you just have to convert this to inch. Okay, so let's review now our solution for this design. Okay, here it is, and we have this given situations, and what we did is we first draw the situation so that we can visualize, and then the next step that we did is to list down the necessary information. So we have the rated power, the speed of the driver, and the speed of the driven, as well as the given one is maximum center distance. Okay, so if it's maximum, then that means that all other values below this, uh, this, I mean, all other values that's below this maximum values would would do the job. Okay, so that's also the same true for this d sub 2 maximum. That's the given. Okay, and when we say design, then we are going to specify the diameters, the belt specs, and the number of belts, of course. Okay, and the next step that we did was to solve for the available parameters. Like for example, if we can solve for the diameter of the driver using the speed diameter relations. But you notice that since this is maximum, then we just have to assume some values right here, because um, if you use this value, then probably we might get some problems along the way. I mean, along the computations. So that's why it's better to not really get into this limit. Okay, so just to make some allowance. Okay, so that's D1, and we solve that, and this is 188 mm, and of course we also round down or round up. That depends upon you, the designer. As long as in the end you can you can do the job, or you can do the required function. Okay, and we also solve for the speed ratio. Okay, so the next one is to determine the type of belts. So to do that, we need the design power, which is multiplied. Which is just a product of the rated power from the motor and the service factor. And the service factor is taken from the tables, and we obtain this value 9,694. Okay, now that we have this design power, then we go to the figure 5. This figure 5, this is the belt selection chart, and right here is the design power axis, and the vertical axis is the RPM of the faster pulley. So we just project a line, and we select the region whichever this point intersects or lies. Whichever this intersection point lies. So if it lies in this A, then you have to select the A. If it lies in the B, then we have to select the type B. Okay, what else? Then the next step that we did is to solve for the belt length. And again, since we have the maximum center distance of 1118 mm, then we can just select we can just select some lower values just to make allowance. Right here using 1000 mm, so we obtain this belt length. L is equal to 107.57 inches, and of course we have to select to some standard lengths. And right here we can use 105 or 112 depending upon you. But right here we'll just use 105. Okay, 105, and that's our standard length. And then after that we determine the number of belts. So how many belts do we need? So we use these equations, the design power divided by the corrected power capacity. So again, even though these are the same powers, this one is referring to something like the load side. Okay, from our ABE161. This is the load side, and this one is the resistance side, or the capacity. Okay, and this corrected power capacity is a product of the power capacity per belt times some correction factors. Okay, and this arc of contact correction factors, this is obtained using table 9. And of course we need this value right here, the arc of contact in degrees, which is computed using these equations. So we computed this, and this is 174.3, and here's our correction factor. And then the next step that we did is to solve for this C sub L correction factor for the length, and that one is obtained using table 10. So since we have the length designation already, then we just project a line, and of course we have, since we solve for type B, then this will be the correction factor. Okay, so once we have all the values, then we just substitute, and then we solve for the number of belts, and we obtain 2 belts. Okay, and then later, in the final step, we have to provide a summary in terms of the belts. So what's the type of the belts, what's the length of the belts, how many number of belts, and what's going to be the pulley, or in terms of specifications. Okay, so that's all. But again, we are just using the PAS 301. But in practice, if there's a manufacturer's catalog, then also you might want to try using their procedure, and I think it will be the same except that for the values of the tables and charts. Okay, so uh, in the next video we will discuss the flat belt drives. All right, so another type of belt drives, but this one is flat belt drives. Okay, so see you in the next video.